Hello, good morning. You're welcome to today's class of Sapo Okechukwu. You're welcome. Good morning. How are you today? Good morning. Who is online today? Please, can you signify? Let's know who is online. Make sure you subscribe to this channel. Give it a thumbs up. Good morning. All right. You're welcome, Sapo Okechukwu. All right, so we are going to continue from where we stopped yesterday. Good morning, everyone. You're welcome to today's class. This is Jossy Science Academy. So today we are going to continue from where we stopped previously yesterday on machines. We went into mechanical energy and we went to machines. We defined machine as a device or tool which allows a force applied at one end to overcome a resisting force at another end. Now we went ahead to state the examples of machine. We have some of the examples of machine that we use in our homes. We have pliers, wheelbarrow, screw jack, wheel and axle, the wedge, scissors, and so on and so forth. Then there are some things we also explained yesterday that we use in describing machines. We have the load, the effort, mechanical advantage, velocity ratio, and the efficiency. And we also derived a relationship between efficiency, mechanical advantage, and velocity ratio. And that relationship is the efficiency is equal to what? Mechanical advantage over velocity ratio. Then because efficiency is expressed as a percentage, we can now say multiply by 100 what? Percent. Okay. Now this formula will actually help you to understand problems surrounding what? Or involving machines. Now you must not forget that the efficiency of a workable machine or a machine that is in use is never 100%. What am I trying to say? It cannot be 100% efficient. Why? It's because of the useless work done against friction in the moving parts of the machine. That is the reason why we need to do what we call lubrication. We need to reduce the effect of friction in the moving parts of the machine to help us work effectively. Is that okay? All right. So let's go into types of machines. Vivi Fitness, wow. Thank you so much for coming. I really appreciate. Thank you so much. All right. So before I go into the types of machine, today's date is 19/12/2024. So I'm going to types of machine. Types of machine. So the first one we're going to look at is the lever. I'll be explaining it as I'm writing them out. All right. So we have the first example of machines that we have here is the lever. This lever is the simplest machine known. Simplest is that we can find this anywhere and we can use this as simple as that to perform a certain text. But it has three classes. It is classified into three. The first one is called first order lever, the second order lever, and the third order lever. So we are going to be explaining them one after the other so they can see the examples of this machine that fall into first order, second order, and what? Third order lever. So in case you see question pertaining this, you can know how you can actually answer the questions. Okay. All right. The first one. All right. All right. So looking at this is the first order lever. So in this first order lever, the fulcrum is between the load and the effort. Now, what is said to be a fulcrum? Fulcrum is like a support that supports these two forces. Okay. For example, if you get a meter rule, I've shown you what is a meter rule before. When you get a meter rule, we also call it knife edge in moment. If you are performing moment experiment, it's called knife edge. So when you get a meter rule, you're going to place it on that knife edge. It will be like this shape of what you have here. When you place it here, you're going to see that the meter is going to balance horizontally on it. Okay, so that is what we call pivot or what? Fulcrum. So fulcrum support that balances an object on a plane level. Do you understand? On a horizontal level. So we want to use it to check the balance point of a meter. We can use what? Fulcrum or pivot. Okay. All right. We can also call it knife edge. Do you understand? Okay. So in this type of lever or in this type of machine, we have that the fulcrum now is between the load and the effort. It is between the load and the effort. That means you're going to put the load on this side and put the effort on this side. Then the fulcrum will be what? Between them. Is that clear? So that is classified under the first order lever. So in any apparatus that you see fulcrum in between them, it is classified as first order lever. I can give you an illustration or an example. One is what? The screw bar, a pair of scissors, a claw hammer, and what? Pliers. These ones are classified under first order lever. You get it now? They are classified under first order lever because the fulcrum is between what? The load and the effort. I want to show you an example. Now, this is a scissors, which is an example of first order lever, right? Now, see what I mean by fulcrum. For example, I want to cut this marker. I will place it here, okay? Or I can get okay, I want to cut this paper. I want to cut this paper. Now, I want to cut this paper. This paper becomes the load, right? I said it becomes the load. Now, see where my finger is. This is said to be what? The effort. Because I'm going to use my energy and place my finger here to be able to cut it. Now, see what I mean by pivot or fulcrum. I think this knot. I think this one that connects them together. This is where the load will be, which is the object. This is the energy, which is the effort, and this is the fulcrum between them. So any type of machine that is this way is classified to be what? First order lever. I don't know if you understand better now. Any object, any machine that is this way, you also have claw hammer and pliers. They all appear in this form. Okay, so it is being classified under first order lever. Do you understand? So we can now classify this under first order lever because this is how it operates. All right, so let's go into second order lever. I hope you are done writing. Lily, hi, you're welcome. Clifford, you're welcome. Linda, good morning. Oh, thank you so much for coming, Linda. I really appreciate it. Thank you so much. All right. All right, the next one we're going to look at is second order lever. All right. The second part of this lever is said to be what? Second order lever. Now, in this one, the load is between the effort and the fulcrum. You can call it fulcrum, you can call it pivot, you can also call it knife edge. I've explained the difference between, I've explained what each of them means, but they mean the same thing in different concepts. Okay. Now, when we have the effort, the load, and the fulcrum, what is between the effort and the fulcrum? It becomes the load. So in this type of lever is classified as second order lever. All right, for example, is wheelbarrow and nutcracker. Let me give you an illustration with a wheelbarrow. When you get a wheelbarrow, carry your load or luggages, put inside of the barrow, right? Now that is where the load is in the middle of the wheelbarrow. Now you're going to use your energy at one end where you have the handle. That is where your energy is applied at one end. Okay. Now the fulcrum, look at the tire where it is being tied with a knot. That becomes the fulcrum, right? So you cannot see in this type of machine that the load is between the effort and the fulcrum, and this is classified under second order lever. Is that clear? Now, don't forget that we did first order lever, and we said that in first order lever, the fulcrum is between the load and the effort. Now, in this second order lever, the load is between the effort and the fulcrum. Okay, so I'm going to bring them together to see the beauty between the three of them in case you're asked questions to distinguish between first order lever, second order lever, and what? Third order lever. Now you can put it down. All right. Are we done writing? Clifford, are we done writing? Clifford, are you done writing? So we can proceed. All right. So let's proceed. All right. Now the next one, which is the third order lever, We have that the effort is between the load and the fulcrum. Now, what do I mean by that? We have our energy, which is happens to be our effort. Now we have the fulcrum, and we have the load. So in this type of machine that is this way, it is classified under third order words lever. Is that is the human forearm, right? Now, if you are holding thing, this is where your energy is coming. This is the human forearm. This is where your energy is coming through. Now, this is what? This is the pivot. This pivot is the connection between this and this. So this is the pivot, which is also known as the fulcrum. Now, this is your energy and this is the load. For example, you want to carry a hefty rod, so you need energy to carry it. By the time you carry it this way, see how your muscle will pop out this way. So this is your pivot, this is your effort, sorry, this is your pivot. So this is classified under what? Third order lever. Then in a nutshell, if you're asked to distinguish between the first, second, and the third order levers, how do you do that? You should know one thing, that use this acronym FLIN, that in first order lever, the fulcrum is between the load and the effort. In the second order lever, the load is between the fulcrum and the effort. And the third order lever, the effort is between the fulcrum and the load. So this is the acronym we are going to use to distinguish what the three types of levers with their examples. Is that clear? All right, so we are going to move into the next type of machine. So copy fast, let's proceed. Veronica, you're welcome. Are we done so that we can proceed? If you are done, please indicate. Let's go to the next one. Now, so let's move to the next one. It's blurring. You can check your network. All right, so put it down. Let's. All right. So let's look at the pulley system. The pulley system, that is number two part of the machine. They are often used in construction sites. Pulleys are often used in construction sites to raise or lower heavy loads. Now, you know what I mean? The most practical system of pulleys is called the block and tackle system. Now, in construction sites, if you want to take a heavy load up, maybe you're building a two-story building, so you need to take that heavy load up or bring it down. So you're going to use what? The pulley, right? Now, this is an example of block and tackle system. In this type of pulley, we have this what? The number of pulley. This pulley 1, 2, 3, and what? 4. All right. Now this is the energy, that is the effort of whatever thing you're carrying. Now this is what? This is the load itself. If you want to carry this object up, you're going to put it here as a load, then carry it to wherever you want to take it to. Do you understand? So this is an illustration of what a block and tackle system. Now, what does this have to do with us, which are working on machines? The relationship between this is that the number of pulleys is equal to velocity ratios. For example, if you have the number of pulleys here, that automatically gives us the velocity ratio of this particular pulley, this particular block and tackle system of pulleys. Now we are going to look at the pulleys we have. We have 1, 2, 3, 4. So in this type of diagram, our velocity ratio is equals to what? 4. Now the essence of these different type of machines we are looking into is for you to know the velocity ratios of this machine. Then you are using that application of that velocity ratio, then put it in our main um, um, machine formula, the one that has efficiency, mechanical advantage, and velocity ratio, right? So you're going to put it in there to find the unknown. Either you're looking for the load or you're looking for effort. Do you understand? So in these different types of machine you're going to be discussing today or maybe tomorrow, you're going to be seeing different types of velocity formulas for velocity ratios. Then we use that and relate to the main formulas that we already know. We'll solve problems relating them. I hope that is clear. All right. All right. So let's go to the next one.
Okay.
All right, just take down the question. Let's solve. Clifford, are you done? All right. Clifford, have you done yesterday's assignment? Have you done yesterday's assignment? If you know you have done yesterday's assignment, say hi. Tell Goma, you are late. Have you done yesterday's? Okay, I've done yesterday's assignment, okay? And I didn't see your answer in the comment section. I said you should go and drop it there. My community. Go to my community in the comment section, drop your answer there so I can confirm. All right. Okay, then you go. I've done your assignment. Okay. All right. So let's look at this example on the board. Okay, it dropped. It's okay. I will check. Then you go, ma. Clifford, yes, but I want us to be dropping that community tab. Just go there and drop it so that I can see it there. Other people will see that you have done yours. Okay. All right. So let's look at this question on the board. The question says, the velocity ratio and efficiency of a system of pulleys are 6 and 80% respectively. Let me go again. The velocity ratio and efficiency of a system of pulleys are 6 and 80% respectively. How much effort is required to lift a load of mass 120 kilogram with this machine or with this system? Now we are given that G is equal to 10 meters per second square. I told you that the number of pulleys in a pulley system is equal to the velocity ratios. Now in this question, we are told that this velocity ratio of a system has 6 pulleys. Automatically, it means that the velocity ratio of this particular machine is equal to what? 6. Is that okay? The number of pulleys is equal to the velocity ratio. Now, we are going to say that my velocity ratio here automatically is equal to what? 6. Then efficiency is 80%. All right. We are looking for effort. That is capital E. Right? Now, how much effort do we need to raise a load of what? 120 kilogram. I told you yesterday that you must concentrate on the values given to you, even if they mention load. But they did not give you, because load is a force. They give you the mass of the load. So there is need for you to convert it to force, which is in Newton. Do you understand? Okay, so I have mass of the load to be 120 kilogram. And we are given acceleration due to gravity to be 10 meters per second square. Then the next thing we are going to do is to find the load. How do we get load? Load is equal to weight, and weight is equal to mass times gravity. So I'm going to say that load is equal to m what? G. That is 120 multiplied by 10 is equal to 1200 Newton. So we are working with this now as the load. So the next thing we are going to do is to use our efficiency formula to solve our velocity ratio, because we can't just look for effort without looking for mechanical advantage, because that is where the relationship between them connect. So I'm going to say that efficiency is equals to mechanical advantage over velocity ratio multiplied by 100%. Okay, so let's substitute into what we have. My efficiency is 80, and I told you yesterday that because I have multiplied by 100% here, I don't need to say 80 over 100 again. Is that clear? So don't make that mistake. Then this is equals to MA divided by what? 6. Then multiply by 100 over what? 1. Then if I go down, I'm going to say that this is 80 over 1 is equals to 100 times MA is going to give me 100 MA, right? Then I divide by what? By 6. Because I'm looking for the coefficient of MA, I'm going to say cross multiply. Then I do cross multiply. 100 MA is equals to what? If I say 80 multiplied by 6, what do I have? 480. Now, what I'm going to do is to find the coefficient of MA by dividing both sides by what? 100. If I divide by 100, okay, I divide by 100. This cancels this. So my MA is equals to 480 divided by 100. So what do I have? I can say 480 divided by 100. What do I have? I have 4.8, right? But don't forget that mechanical advantage is equals to load over effort. So what's my mechanical advantage? 4.8. Now is equals to what's my load? My load is 1,200. Okay? And divided by what? By effort, right? Then I will do cross multiply by saying 4.8e is equals to 1,200. Because I'm looking for the value of E, I'm going to divide the both sides by the coefficient of E, which is 4.8. So my E is equals to 1,200 divided by 4.8. All right, let's see what you're going to have. Now my answer becomes 250 Newton. I hope you understand that. So if you have this type of question, you must note that the number of pulleys in a pulley system is equal to the velocity ratios. So once you are given that, you just state that as a velocity ratio. In this question, we are given this as number of pulleys. So that automatically becomes a velocity ratio. Now we have the efficiency to be given as 80%, and we're looking for the effort, which is this, right? But we don't even have the load, we're giving the mass of the load. So my mass of the load is 120, and I'm giving as ratio this to gravity to be what? 10. So what am I going to do next? I'm going to find what? My load. By doing what? By saying that load is equal to mg, right? Now what's my mass? My mass is 120 multiplied by what? G, which is 10. Okay? So my answer becomes 1,200 newtons. All right. Now I can't just look for effort straight without looking for the mechanical advantage. So avoid making mistake. So what I'm going to do is to substitute the values and make MA the subject, of which I got my answer to be 4.8. Then the next thing to do is to make E the subject, because mechanical advantage is equal to load over effort. By the time I put in the value of effort, and my answer becomes 250 newtons. I hope that is clear. All right, put it down. All right, put it down. Let's proceed. Clifford, do you understand? Tenny Goma, is it well understood? Do you understand? Please give it a thumbs up, okay? All right, Clifford, are we done? Let's move to the next one. All right, so let's look at another example. All right, so put it down, let's solve. Put it down, let's solve. Are we done? Let's proceed. All right, let's solve. A block and tackle system is used to lift a load of 200 Newton through a vertical height of 10 meters. If the efficiency of the system is 40%, how much work is done against friction? Now, in this type of question, what we are going to do, looking for work done against friction. Now, before we can get work done against friction, we need to get the work input. The work input. Remember that yesterday I told you that efficiency can also be defined as the work output divided by the work input. Okay, so for us to get the work done against friction, we must get the work input. From the values given to us, we can calculate our work output. All right, so let's state our values. My load is given as 20 Newton. Then distance moved by load is given as 10 meters. Efficiency is given as 40%. Then you're looking for work done against what? Friction. Work done against friction. Now, how do we get this? The first step to do or to take is for us to get the work output. I tell you that the work output is equals to load multiplied by distance moved by what? Load, right? Then using this efficiency formula, that efficiency is equals to what? Work output divided by what? Work input. Then multiply by 100%. Is that okay? All right. So let us get the work input because you're looking for work done against friction. By the time you get our work input, it will help us to calculate the work done against what? Friction. All right. So let's go. My efficiency is 40 over 1, then is equals to my work output is load multiplied by distance moved by load. And what is my load? My load is 20. Distance moved by load is what? 10. Okay. Then is equals to the work input multiplied by 100 over 1. Okay. Now this is 40 over 1 is equals to 20 times 10 is 200 multiplied by 100. What do we have? We are going to have what? We're going to have 20,000 So you divide both sides by what? Work inputs, right? So we do cross multiply. That work input is equals to 20,000 over what? 40, right? So by the time you divide it, the work input is equals to 500 watts joules, right? Is equals to 500 joules. Now, if I want to sum up this work output, I'm going to say that work output is 20 multiplied by 10, then it's going to give me 200 watts joules. Hope you understand. If I proceed. Alright, so for us to get the work done against friction, work done against friction is equals to work input minus work output. Okay, the work done against friction is work input minus work output. That is 500 minus 200, and the answer is equals to what? 300 joules. So the work done against friction becomes work input, which is what we have gotten to be 500, minus work output, which is 200. We now must subtract it to get our answer to be what? 300 joules. Is that clear? All right. Please, do we understand what I just explained? Osage, you are just coming. You say you don't understand. This is the, I think this is the second example I'm solving under this. All right, so are we done? Osage, you can watch the video after now, okay, so you understand better. Are we done? Let's go to the next one. Are we done? I want to go to the next one. Next type of machine, which is an inclined plane. Clifford, Tenny, Goma, are we done? So let's look at the next type of machine, which is inclined plane. Number three. All right, put it down. Let's solve. Put it down. Let's solve and solve. Copy fast, please. All right. Are we done writing Osage Clifford? Then you go, ma. Are we done writing? All right. So let's proceed. Let me explain this. Okay. So the next one is inclined plane. Inclined plane is a machine used to raise heavy loads such as drum of oil up a slopy plank to the high floors of lorries. The slopy plank is an example of an inclined plane. Now this is an inclined plane. So what do I mean? This plane is inclined here. This is the ground. This plane is inclined. This is a plank. Inclined. This is a high floor of lorry. High floor of lorry. Okay? So it's just like you're using a plank to keep on the ground and extend it to the floor of a lorry. Then if you want to carry a drum of oil, you now roll it because it's very heavy that 10 hefty men cannot carry. So they need to use a machine which is said to be an inclined plane. They are going to incline it from the ground to the what, floor of a lorry. They will now roll it up to the floor of a lorry. Do you understand? So as they're rolling it up, the energy moved, which is the effort, is going this way because they're pushing it up to the floor of a lorry. Okay, so this inclined plane makes an angle called theta with the horizontal. All right, so the distance moved by this effort is L because we are moving the drum of oil through this plane. That is L, right? While the distance moved by load is the what? Height, because the load, which is the drum of oil, has moved from here to the floor of a lorry. Now, there's one other thing you need to know is that we can actually resolve this. We can resolve this into horizontal and vertical components. Now, this object that is going this way, there is also a force that is going opposite, which is frictional force, right? Now, we can resolve it to the vertical component, and vertical is what? Mg sine theta, right? We can also resolve it to the horizontal component, which is what? Mg cos what? Theta. This is the mass of the object, and the reaction is going this way, while the weight is acting this way. Do we understand? This is just like other coefficients of limiting friction. You see that the weight of the object is acting down, the reaction is acting up. Then the object is moving in this direction where the frictional force is acting in a direction opposite to the direction of the motion. So, because we are pushing this in an inclined plane, such forces can be experienced in this type of diagram. Okay, so this is a coefficient of limiting friction applied to inclined plane machine. Now, if you are drawing the object, or which is the drum of oil, this is the object of certain mass, right? Now we can resolve this object to the horizontal component, which is this, vertical component, which is this. And there is also a force that is acting opposite to the effort, which is said to be frictional what? Force. Is that clear? Now, what again do we need to know? The velocity ratio is the distance moved by effort, which is L. I told you the effort is being pulled this object from this distance to this distance over distance moved by load, which is what? H. All right. Now we can also say that velocity ratio is the length of inclined plane, that is L, over the height of inclined plane, that is this H. Right. In a nutshell, we can say that 1 over sine theta is equals to VR. So this is opposite of sine, and sine is what? Opposite over what? Adjacent, right? Sine is opposite over what? Hypotenuse. But because it is opposite of over it, so it becomes inverse of sine. So VR is equal to 1 over sine what? Theta. That is, in case you are given the angle of an inclined plane, the angle in which the plane is being inclined, have to find the velocity ratio. You can use this formula to get it. But if you are not given, you can use the length of inclined plane and the height of inclined plane to get your velocity ratios. Or you can ask to find the force acting on this object that is on the inclined plane, which is the force pulling it up or the force acting on it. Is that okay? So we're going to look at few examples under this inclined plane so that I can understand how we can approach questions using inclined plane. All right, put it down. right. Also, you say, why are we using sine instead of cos, right? Now, if you remember that sine theta, sine is opposite over what? Hypotenuse, right? Opposite over hypotenuse. Then this angle, the opposite to this angle is h. Okay, why the hypotenuse is what? L. So it's supposed to be what? H over L, right? But now, why are we having opposite? Because why are we having inverse? Because the velocity ratio is distance moved by effort over distance moved by load. Do we understand? In velocity ratio, we are going opposite of what we have, which is supposed to be what? L over what? H. That is for velocity ratio. Distance moved by effort first over distance moved by what? Load. So it is inverse of what? The sine. Because sine is h over L. While velocity ratio is what? L over what? H. So rearranging it to be in form of velocity ratio becomes inverse of the what? Of the sine. So that's why the velocity ratio is 1 over sine theta. Do you understand? We are considering the angle, the height, and the what? And the length. And opposite over hypotenuse becomes what? Becomes sine. But because we are considering the velocity ratio, which is distance moved by effort over distance moved by load, that is L over H. So rearranging it to be in form of velocity ratio, it is now the same thing as saying inverse of sine is going to give us L over H. Is that clear? All right. Then you go, can you see now? Osage, is it clear now? Are you cleared? No, VR is not always inverse. It's just for this inclined plane based on the way the diagram is, okay? So in the inclined plane, the velocity ratio is inverse 1 over sine theta just because of the way the diagram is. Look at sine theta is opposite over adjacent. And the opposite to this angle is H, while the adjacent is what? L, okay? But velocity ratio is distance moved by effort over distance moved by load. That distance moved by effort is L, while distance moved by load is H. Okay, so for us to be able to do that, what we need to do is to do inverse of sine, because it's only inverse of sine theta that is going to give us L over H, and that is what we just did. All right, can we copy fast? Let's move to examples. All right, so let's look at examples under this inclined plane so you can understand it better. All right, so put it down. Let's solve. All right, are we done writing? All right, the question says an inclined plane of an angle 15 degrees is used to raise a load of 4,500 Newton through a height of 2 meters. If the plane is 75% efficient, calculate the velocity ratio of the plane and the work done on the load. Now, looking at this question, the first thing to state is to state our parameters. We are given angle, that is theta, to be 15 degrees. Okay, we are given a load of 4,500 Newton, that is the force. Then the load is 4,500 Newton. Okay, then through a height, distance moved by the load is 2 meters. Okay, and the efficiency is 75%. Now, what are we looking for? We're looking for the work, the velocity ratio, yes, one, and the work done on the load. We're looking for velocity ratio. Now, from our formula, velocity ratio is equals to 1 over sine theta. Okay? Losses ratio is 1 over sine theta. Now, what do we mean? You just have to substitute that VR is equals to 1 over sine. My theta is what? 15. So with your calculator, we are going to say sine 15 is going to give us VR is equals to 1 over 0.2588, right? Now let's divide it. We're going to have 33.86. Remember, velocity ratio has no SI unit. Now we are done with that. The next thing we are looking for is the work done on the load. Which one is work done on the load? Work done on the load becomes the work input, because you are doing work on the load. So that is your energizing on the load, becomes work input. Now, efficiency is equals to work output over work input. Then multiply by 100%. Okay? So my efficiency is 75 is equals to the work output. Remember that work done is force times distance. So the output is the force, and the distance moved by it is 2 meters. This is 4,500 multiplied by 2, then divided by the work input multiplied by 100 over 1. Okay, so let's go. We're going to say 4,500 multiplied by 2, then multiply by 100. My answer becomes 900,000 divided by work input, right? So I'm going to divide both sides by the coefficient of work input, which is equals to 900,000 divided by what? 75. So my answer becomes 12,000 joules. So my work input is 12,000 joules. I hope that is clear. Put it down. All right, do we understand? All right. So we can proceed. I'm going to give you a question to try for me. Let's see where I have an idea of what you are doing. I want to give you a question to solve. Classwork. Let's see. All right. All right. So see how you can solve this. All right. You have a few minutes to do that. Solve it and yes. Solve it and solve your and send in your answers. All right, Osaze, you say it's quite hard. Okay, but we're able to attempt it. Do you attempt it? Let me see if you have an idea. Did you attempt it? If you were asked to calculate the force parallel to the plane, which force is parallel to the plane that is required to push a load of 120 Newton uniformly up the plane? Which force is parallel to the plane? That is one thing that you must ask yourself. Which force is parallel to the plane? Look at the diagram that we drew. The diagram, we have this, and we have this, right? This is the object that we are pushing uniformly up the plane. So this is my energy, this is my effort, sorry. This is my load acting down, right? So this is the plane, that is this plane. Distance moved by the effort is this, distance moved by load is this, right? Force parallel to the plane becomes the effort. That is just it. In this type of question, what you're looking for is the effort. And before we can solve for the effort, you must get the velocity ratio, you must get the mechanical advantage before you think of solving for the effort. Once you hear a word, a question like the force parallel to the plane, it is the effort that you're looking for. Is that clear, Osagi? All right, let me solve. All right, the first thing we are going to do is to state that our theta is 30 degrees, right? Now my efficiency is 50%. Which force are we looking for? Looking for the effort. Okay, but we have a load of 120 Newton. Of 120 Newton, right? Now for us to get the velocity ratio, the formula is VR is equals to 1 over sine theta, right? Then VR is 1 over what? Sine 30. You already know that sine 30 is 0.5. So VR is 1 over 0.5 and VR is equals to 2. Is that clear? All right. So the next thing is to solve for the mechanical advantage. Efficiency is equals to MA over VR multiplied by 100%. Okay? Then let's go. Efficiency is 50 over 1. The first thing is to get our MA divided by 2, which is the velocity ratio, multiplied by 100 over 1, right? Then if I do cross multiply, I'm going to have that 100 is equals to 100 MA, right? Now what do I do next? I divide both sides by the coefficient of MA, which is 100. All right, this cancel this, right? Okay, so it means that my mechanical advantage is equals to 1, right? Now remember that MA, which is mechanical advantage, is also equals to load over effort. That means 1 is equals to, what is my load? My load is 120 divided by E, which is the effort, right? I'll say this is over 1, cross multiply. That means the effort is equals to 120 Newton. Is that clear? Our effort is equals to 120 Newton. So which is the force parallel to the plane required to push the load uniformly upwards the plane? All right. No, Osage, you're not resolving to the horizontal, okay? The essence of that theta there is for us to get the velocity ratio. We are not resolving. We are not resolving. Now let me give you another question on this to see if you can be able to attempt it. Still under velocity ratio. Clifford, do you understand? All right, you can look at this question and see how you can solve it. Still similar to what we did before. See how you can solve it, okay? And drop your answer in a few minutes' time. We'll soon end the class. We have a few minutes to go. After this question, we'll just end the class. All right. Asagwe, your answer is 133.33 newtons, correct? Clifford, what's your answer? You don't solve it. What's your answer? What's your answer? All right, let's work it out. Let's see what we have. Let's solve it together. Okay. A 2 kg mass is to pull up a slope inclined at 30 degrees to the horizontal. If the efficiency of the plane is 75%, sorry, calculate the force required to pull the plane. All right, so the first thing we are going to do is to know that we are giving the mass of the load, not yet the load, okay? So ml, which is the mass of the load, is 20 kilogram. All right, incline at angle theta to be 30 degrees. Okay, and we have that efficiency to be 75%. Then we are giving G to be 10 meters per second square. Okay, so what are we looking for? Looking for effort. Okay, now we cannot solve for effort without looking for the velocity ratio and the load itself. So I can start with the load. Load is m what? Mg. That is 20 multiplied by 10 is going to give me 200 Newton, right? That is the load. Now the next thing we are going to do is to find the velocity ratio. That is 1 over sine theta, which is 1 over sine 30, which is 1 over 0.5. Okay, and VR is equals to 2, right? Then the next we are going to do is to find our MA using the efficiency formula. Efficiency is equals to MA over what? VR multiplied by 100%. Now what's the efficiency? The efficiency is 75 over 1 is equals to MA over VR, which is what? 2 multiplied by 100 over what? 1. Now what do we do next? We multiply by saying this is 150 is equals to 100 MA. All right, I divide both sides by what? 100, 100. Therefore, my MA is equals to 1.5. Hope I'm not mistaken. Let us say 150 divided by 100. That is 1.5. Okay, let's go. MA is equals to load over effort. Now my MA is 1.5 is equals to, my load is 200 over what? E. Therefore, my effort is 200 divided by 1.5. Okay? So I'll say 200 divided by 1.5. So my answer is equals to 133.33 newtons. So the answer to this question is 133.33 newtons. Okay? Yes, Osage, you are correct. Well done. All right, so we're going to end this class here. I'm going to put up an assignment in the community where I did yesterday. So you go there and look up for your assignment, you solve it, and type in your answers. Okay, so we are going to meet tomorrow same time. Make sure you do your assignment, make sure you copy down your notes, make sure you read your books. The more you do that, the more you learn physics better. I will see you next time in my next class. Bye for now.